All right, today we will be going through the June 2011 end of year exam for Year 9. We'll start with question 1. In this question, choose your answers from the substances listed below. Each substance may be used once, more than once, or not at all. And we've got a bunch of different substances here that we've learned about over the course of this year. So this question is pretty synoptic. It's going to bring together a lot of the different topics that we've talked about this year. So A is a solid, non-metallic element. So just using the information we have there, we can rule out quite a lot of things. It's an element, so we know it's not going to be something like carbon monoxide, sodium hydroxide, copper 2 chloride, because those are compounds, okay? Non-metallic, so it can't be magnesium. So our options are phosphorus, bromine, argon, and hydrogen. Hydrogen and argon are both gases. Bromine's a liquid, so it has to be phosphorus. B makes up about 1% of the air. We know that there's carbon dioxide in air, but it has a bit more than 1%. And the only other one in there would be argon. Dissolves in water to give a solution that conducts electricity and decomposes to give a pink-brown solid. So we know something that dissolves in water to give a solution that conducts electricity. That's going to make an electrolyte, and we know that has to be an ionic compound. So if we look back up at our list, we have 2 ionic compounds, sodium hydroxide and copper 2 chloride. So the other piece of information is it decomposes to give a pink-brown solid. A pink-brown solid, that's going to be copper, so we know that it's talking about the copper 2 chloride. Is a common bench alkali with a pH of a value about 13. pH of a 13 tells us that is a strong alkali, so we're looking for something that's strongly alkaline, and hopefully we remember that the ion that makes things alkaline is hydroxide, so that one's going to be sodium hydroxide. Will conduct electricity when solid. The only substances we've learned about this year that conduct electricity when they're solid are just metals by themselves. So not ionic compounds, but metals. So if we look up here through our list, there's only one metal on that list, and that's magnesium. When mixed with air, burns with a squeaky pop. This one seems to be something everyone seems to be pretty familiar with. Squeaky pop test tests for hydrogen. Gives a yellow flame and produces white smoke when burned in oxygen. So we learned and saw about quite a few different elements and the way that they burn in oxygen. So this is something you just need to learn off by heart, the different observations for that. But the yellow flame and a white smoke is describing phosphorus. Is used in some fire extinguishers. That is carbon dioxide. Again, something you just kind of need to know off by heart. Is one of the only 2 liquid elements at room temperature and pressure. We have 2 elements that are room temperature and pressure are liquids, bromine and mercury. Mercury is not an option, so it must be bromine. And the last one turns lime water milky. Lime water is used to test for the presence of carbon dioxide. Question 2. Complete the table below by filling in the empty spaces. Magnesium has been fully completed for you as an example. So this looks at atomic structure, okay? Figuring out the number of subatomic particles in different elements and ions. So we can look and see magnesium gives us some information here. So for example, we've got the mass number, atomic number, number of protons, number of neutrons, number of electrons, and the electron configuration. So that's an example for us. Hopefully you remember the mass number is the number of protons plus neutrons. So you add those 2 together. And the atomic number is the number of protons. So if we know the number of protons, and we know the number of protons and neutrons, we can subtract these two to find the number of neutrons. And you see with magnesium, protons and atomic number are the same. Protons and neutrons add together to give us the mass number. To find the number of electrons, if it's an atom, it's neutral, so the electrons and the protons are exactly the same. And we'll talk about what it is in an ion when we get to the end. So the next one we're looking at is a calcium atom. So it gives us the mass number is 40 and the atomic number is 20. So remember, the number of protons and the atomic number are exactly the same. So 20 protons, an atomic number of 20 means we have 20 protons. The number of neutrons is equal, we can find from the mass number. So if the mass number is 40 and we have 20 protons, we subtract 40 minus 20 and we get that we have 20 neutrons as well. Here it's telling us that the number of electrons is the same as the number of protons, which makes sense because it's an atom, so the charge has to be 0. And we need to figure out the electron configuration. So if you remember, 2 electrons can go in the first shell, 8 in the second, 8 in the third, and then the most you need to worry about in the fourth shell for this year is there will only ever be 2 in there at the maximum. So we have 20. If we have 2 in the first shell, 8 in the second shell, that takes us up to 10. 8 in the third shell takes us up to 18, and so we have 2 left over. So 2, 8, 8, 2. Nitrogen atom. Here we're not given the mass number or the atomic number, but we know the number of protons, neutrons, and electrons, so we can figure those out. Remember, the number of protons and the atomic number are exactly the same thing. So if we have 7 protons, we have an atomic number of 7. The mass number is equal to the protons plus the neutrons. So 7 protons plus 7 neutrons gives us a mass number of 14. And again, we have 7 electrons. So if we figure out our electron configuration, we'll put 2 of them in the first shell. The second shell can hold up to 8, but we only have 5 more, so it's just going to be 2, 5. Now a sulfur ion is just a little bit trickier because of that 2 minus charge. So again, we've got the mass number and the atomic number, and remember, the atomic number and the number of protons are exactly the same, so 16 protons. We take the mass number minus the atomic number to find the number of neutrons. 32 minus 16 means that we have 16 neutrons. Now, if it was a sulfur atom, we would have 16 electrons, but it's not. It's got a 2 minus charge because it's an ion. So something has a 2 minus charge, it means it's gained 2 negatives. It's gained 2 electrons. So it has 2 more electrons than what it would normally have. So instead of 16, it's gained 2, it has 18 electrons. Okay? We still use those 18 electrons to do our electronic configuration in exactly the same way. 2 in the first shell, 8 in the second shell takes us up to 10. 8 in the third shell takes us up to our 18, but it's important for an ion, you have to put a charge on the electron configuration. So don't forget to put that 2 minus charge for the sulfur ion, or the sulfide ion is really it's more appropriately called. Part B has us use our charges that we should have learned to write good formulas for ionic compounds. And remember that when we have an ionic compound, the overall charge always has to be equal to 0. So potassium sulfide, potassium has a charge of +1. Sulfide has a charge of -2, so we need 2 potassiums for every 1 sulfur to get it to add up to 0. So we have K2S. So sodium iodide, we have sodium, which has a +1 charge. We have iodide, which has a -1 charge. Okay, and again, you need to memorize these or at least know how to find them on the periodic table. +1 and -1, those already cancel out, so it's just NaI. Lithium nitride, you should know that lithium has a charge of +1. Nitrogen has a charge of 3-. And we can actually figure some of these out from our periodic table. So if we look at our periodic table, everything in our first group has 1 outer electron. The group number can tell us that. So we have 1 outer electron. So we form an ion by losing that electron. So everything in this group has a charge of +1. Everything in this group has 2 outer electrons. We'll lose them and have a charge of +2. Everything here has 3 outer electrons. We'll lose those and have +3. Here we have 5 outer electrons. So it's easier to just gain 3. So that will give us a -3. Here we have 6, so we gain 2, 7, so we gain 1, 8, we're already full, so we don't gain anything. So anything in this group has that charge. So lithium has a charge of +1, Nitride has a charge of -3, and that can help you to remember that. So, +1 and -3, we need them to add up to each other. So we need 3 lithium so that we have a total charge of +3. So we write that as Li3N. Iron 2 oxide, iron 3 oxide. Remember, this 3 tells us the charge of the iron. It doesn't tell us how many irons we need. It just tells us the charge of the iron. So we have Fe3+ and O2-. So here, we can't easily turn one into the other one. We can't turn 3 into 2, we can't turn 2 into 3, so we have to change them both. So you want to think of the smallest number that both 2 and 3 go into, and that would be 6. So if we need +6, we need 2 irons. If we need -6, we need 3 oxygens. So we have Fe2O3. 2 times 3 gives us 6, 3 times 2 gives us 6, total charge of 0. Barium hydroxide. We have barium, which is Ba2+, and hydroxide, which is OH-. So in order to get those charges to add up, we need 2 hydroxides for every 1 barium. And this is an area where a lot of people lose marks because they do this, BaOH2. But this doesn't say we need 2 hydroxides. This says we need 2 hydrogens, which isn't what we're trying to say. So remember, if you have a polyatomic ion or an ion with more than 1 capital letter, you need to put it into brackets. So we need Ba, OH in brackets, and then a 2, showing we have 2 hydroxides and not just 2 hydrogens. Oops, sorry about that. Magnesium hydrogen carbonate. Magnesium is our Mg2+. Hydrogen carbonate is HCO3-. -1 plus 2, we need 2 of these so that the charges add up. And again, we've got more than 1 capital letter, so we need to put it in brackets. So Mg brackets, HCO3 brackets 2. So we have 2 hydrogen carbonates for every 1 magnesium. And the last one, ammonium sulfate. Ammonium is NH4+. Sulfate is SO4 2-. +1 and -2, we need 2 ammoniums to get a charge of +2 to cancel out that -2. Since we have more than 1 capital letter, this goes into brackets. And we need 2 of them. Now sulfate doesn't go into brackets because we only need 1 of them. So we only use brackets if we need more than 1 of the polyatomic ions. So we get NH4 2SO4. Question 3. This question concerns the structure and bonding of ionic compounds. So sodium chloride is a typical ionic compound. By considering its structure and bonding, explain the following observations. So this is important. We need to talk about structure and bonding in our answer. All right. Explain the following observations. It will only conduct electricity when molten or in solution. Hopefully remember that for something to conduct electricity, it has to have charged particles, and they have to be free to move. And in an ionic compound, when it's molten or in solution, the charged ions are free to move. So when molten or in solution, the charged ions are free to move. Not electrons, okay? Ions. We are in an ionic compound. Our charged particle is ions. All right. It has a very high melting point. So when we're melting an ionic compound, you have to remember we're separating those ions. We're pulling those ions apart from each other. So we have to overcome the attraction between those ions. We have to break that bond between those ions. And that takes a lot of energy. Anytime we talk about the melting points of ionic compounds, we need to talk about those attractions. So it's because there are strong electrostatic attractions between the oppositely charged ions in the giant lattice. So it takes a lot of energy to separate them. Anytime we talk about the melting points of ionic compounds, it's important that we mention the strong electrostatic attractions and the fact that these attractions are between oppositely charged ions. All right. It will dissolve in a polar solvent, such as water, but will not dissolve in a nonpolar solvent, such as volatile. So this is a topic that we'd come back to in year 10, but it's important to know a polar solvent has poles like a magnet. A nonpolar solvent doesn't. So in something like water, we have a slight positive end and a slight negative end because the electrons aren't evenly shared. So an ionic compound has the charges. Those charges will be attracted to the partial charges in water, but they won't be attracted to the neutral volatile. So the charged ions will be attracted to the partially charged water molecules, but not to the neutral volatile molecules. Okay? So think about it like a magnet. All right? The water is like a slight magnet that attracts the positive and the negative ends. The volatile is not magnetic at all, so there's no attraction. There's no poles in there. All right. B, the diagram below represents the electronic structures of a fluorine atom, a fluoride ion, and magnesium fluoride. And the spaces use the same method to show the electronic structures of a phosphorus atom, a phosphide ion, and a barium phosphide. So on this side, these are just examples to show us how to do it. So we see that we know fluorine has 7 electrons, so it has 2 in its first shell. It has 9 electrons, 2 in its first shell, 7 in its second shell. To form an ion, it gains 1, which gives it a -1 charge. So we're going to do the same thing with a phosphorus atom. So if we look at our periodic table, we see phosphorus has 15 electrons. Okay, so we have our phosphorus. We need our 15 electrons. So we're always going to have 2 in the first. 8 in the second will take us up to 10, so we'll have 8 in the second. And then we're going to have 5 in the third. So we have our 15 electrons shown, and that's our phosphorus atom. We have 1, 2, 3, 4, 5 electrons in the outer shell. We either need to empty this or we need to fill it up to 8. So we could lose 5 or we could gain 3, and it's going to be easier to gain 3. So we're going to have 3 new electrons in our phosphide ion, but everything else stays the same. So we still have our 3 shells. We still have 2 in our first shell, 8 in our second shell, and our original 5 in our third shell. But now, to form an ion, we've gained 3 new electrons, and we use X's to show, or crosses to show that those ions came from something else. And then if we notice, fluorine atom, no charge, fluoride ion, charge, we've added 3 negatives, so we have a charge of 3 minus. So 1 mark for the electrons, 1 mark for the charge. Now they've shown us magnesium fluoride using the outer shells only. And we can see magnesium has lost electrons, fluorine has gained electrons in this case. And we've got their charges and their symbols down here. So we're going to need to do the same thing with barium phosphide. So we're going to have our barium ion with its outer shell. We're going to have our phosphide ion with its outer shell, both in brackets, and then we'll need charges and ratios. So I like to just get started, get all that stuff out of the way. If we look at our periodic table, barium has 2 outer electrons normally. So to form an ion, it's going to lose those 2 electrons. Once it loses 2 electrons, it will have a charge of 2+, and its next shell in will become its new outer shell. So once it's lost those 2 electrons, it will have 8 electrons left over in its outer shell. And any metal is going to have 8 electrons in its outer shell, except for lithium and beryllium will only have 2, because their second shell is the one with their outer electrons. If they empty out the second shell, they're into the first shell, and the first shell only holds 2. But every other metal will have 8 in its shell once it's lost it to form its ion. Phosphorus, we did on the previous page. We know it starts with 5. Sorry, starts with 5, ignore that one, and it gains 3. So it has 3 crosses, and that gives it a charge of 3-. We already did that one on the previous page. So the last thing to do is to figure out the ratio. Barium needs to lose 2. Phosphorus needs to gain 3. They have 2+ and 3-. Remember, they have to add up to 0. So the only way for this to work out is if barium loses 6 and phosphorus gains 6. So to lose 6, we need 3 bariums. To gain 6, we need 2 phosphides. So we need Ba3P2. And we do that just like we did when we were figuring out the charges. Question 4 is about the periodic table. Periodic table is an essential tool for chemists as it helps to predict the reactivity of elements. Historically, there were 3 chemists whose attempts to arrange the elements into a logical order led to the development of the modern periodic table. Now, we don't learn about the modern periodic table in as much detail as we used to. We don't really learn about the process in which it was developed, but there's still some important pieces of information that we need to know about the periodic table. So in order of what atomic property are the elements arranged, you should know that it's arranged in order of increasing atomic number, or number of protons. All right. What is the name for the horizontal rows, and what atomic information do they tell you? So you should know that our horizontal rows are called periods. Okay, that's where periodic table comes from. And it tells you the row that it's in, the period that it's in, tells you how many shells have outer electrons. So everything in period 1 has electrons in its first shell only. Period 2 has it in the first and second. Period 3 has it in the first, second, and third, and so on and so forth up to period 7. So it tells you the number of shells that contain electrons. What was the name for the vertical columns, and what atomic information do they give you? So our vertical columns are called groups. Everything in the same group has similar chemical properties and trends in its physical properties, and that's because they all have the same number of outer electrons. Okay, so they react similarly. So everything in group 1 has 1 outer electron. Group 2 has 2 outer electrons. 3 has 3, 4, 5, 6, 7, and 8. So the groups tells you the number of outer electrons. All right. B, potassium is one of the alkali metals. Okay, remember our alkali metals are in that first group, group 1. State 3 observations that you would see when a piece of potassium is thrown into a trough of water. This is something that we did. If you YouTube it, you can definitely find some examples of, you can find videos where you can see this if you don't remember exactly what happens. But the important thing is observations are things we would see. Okay, so there are some specific things that we should mention. You can say that it floats or whizzes around the surface of the water. You can say that it dissolves to form a colorless solution. You can say that it melts into a silvery ball. or you can say that it ignites and burns with a lilac flame. Okay, any three of those four will get you the marks. If it asks about lithium and sodium also float and whiz around the surface and dissolve to form a colorless solution. Sodium also melts into a silvery ball, but potassium is the only one that catches on fire because it's the most reactive, at least in the size that we're doing in our experiment. So that's what they'll expect, is that potassium is the only one that catches on fire. Give a word equation for the above reaction. So we know that we're starting with potassium, and we're reacting it with water. Hopefully you remember that when a reactive metal reacts with water, it forms an alkaline solution because it's formed hydroxides, and it forms hydrogen gas. So that's what makes it move around the surface like that. So we get potassium hydroxide plus hydrogen gas. So you wrote it in words, and now we need to write a fully balanced symbol equation for the above reaction. Make sure you're paying attention if it's asking for words or symbols, because even if you had it perfectly correct, if you have the wrong one, it's not going to be right. So potassium symbol is a K, and water is H2O. For potassium hydroxide, we have K, which has a +1 charge, and OH, which has a -1 charge. So those are balanced. We don't need any subscripts. And don't forget that hydrogen is one of our diatomics, so we need H2. Okay, so now the last thing that we need to do is we need to balance it. So remember, balancing is kind of just like guessing and checking. You need to go back and forth between the two sides to make sure you have the same amount of each element on each side. Hold on, let me fix that lighting a bit. Okay, so we have 1 potassium here, we have 1 potassium here, okay, so that's okay. We have 2 hydrogens here, and here we have 3 hydrogens, okay? So this is always going to be an even number of hydrogens. We need to make this an even number of hydrogens as well. So to make this so we have an even number, we need to put a 2 in front of our potassium hydroxide, okay? Now, we have 2 potassiums, so we need 2 potassiums. Sorry, the lighting from the sun is, there we go. 2 potassiums, so we need 2 potassiums. We have 2 oxygens, so we need 2 oxygens, so we have to put a 2 out here. We have 4 hydrogens, and we have 4 hydrogens, so we're totally balanced. Remember, we use little numbers when we look at one formula, the little picture. We use big numbers when we look at the whole equation, the big picture. So now it's completely balanced. Lithium and sodium behave in a similar way when placed in water. Explain why this is the case. Remember, everything in the same group has similar chemical properties because it has the same number of outer electrons. So they react similarly because they all have 1 electron in their outer shell. All right. Chlorine is one of the halogens. Lists 3 similarities between all of the halogens. There are a bunch of different things that we could say here. Okay. They all have 7 electrons in their outer shell. They all form colored vapors. They all react with metals to form salts. And they're all diatomic. So any 3 of those 4 will get you the marks. Those are all things that halogens have in common. Okay. How do the melting points of the halogens change when moving from fluorine down to astatine? So looking at our periodic table, fluorine's at the top of the halogens, chlorine, bromine, iodine, acetine. We know fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid, and acetine is a solid. So as we move down, okay, they're going to melt at higher and higher temperatures. Okay, iodine's melting point is obviously above room temperature, where fluorine's is obviously below room temperature. So we know that as we move down the group, the melting point increases. All right. Question 5 is about acids and alkalis. So acids and alkalis are chemical opposites. This question considers some of their properties. Complete the following table to show the properties of various acidic, alkaline, or neutral solutions. An example has been done for you. So they did ethanoic acid, and it wants to know is it acid or alkaline? What color is it with litmus? What color is it with phenolphthalein, universal indicator, and an approximate pH value? So ethanoic acid is weakly acidic, so it'd be red, colorless yellow 4. So water is neutral. Okay. Litmus is red and acid, blue and alkali, and if you mix red and blue together, you get that it is purple and neutral. Okay. Phenolphthalein is colorless and acid, colorless and neutral, and pink in alkaline. Universal indicator kind of goes the spectrum of the rainbow, so it starts at red, it ends up at purple, so right in the middle is going to be our green for our neutral, and neutral is a pH of 7. Okay, so you just need to know these things about our different indicators and our pH values. Hydrochloric acid is our really common strong acid, so it's strongly acidic. It still will be red with litmus. With phenolphthalein, it's still acidic, so it will still be colorless. In universal indicator, it's much more acidic than ethanoic acid, so it's going to be, you could say, pink or red. Either one of those will be fine. And something that has strongly acidic is going to have a lower pH, so it's going to be closer to a pH of 1 to 2 instead of 4, way down at the bottom of that pH scale. Ammonia solution is our common example of something that is weakly alkaline. Alkalines turn litmus blue. They turn phenolphthalein that bright pink magenta color. Universal indicator. Purple is going to be strongly alkaline, so we're looking at something more blue. And the pH value, the approximate pH value, I would say is somewhere around 11. Okay, not quite up to 14, so 10 to 11 we'll say. Not quite up around 14, but higher than 7. All right, fully balanced symbol equations for the following acid reactions. So you need to learn the patterns for acid reactions. What happens when an acid reacts with a metal, when it reacts with an alkaline or a base, what happens when it reacts with a carbonate or a hydrogen carbonate, and with ammonia. So you need to remember those patterns. So copper to, and here it says fully balanced symbol equations, that's important. Copper 2 oxide is a metal oxide. Metal oxides are alkaline. And sulfuric acid. So we have an acid and an alkaline. We're going to make a salt and water. So to remember, to figure out the salt, we take the first part of our base, which is going to be the metal, so copper 2. And then we take the part of the acid that's not the hydrogen. So sulfuric acid makes sulfates. So we have copper 2 sulfate. And our other product, like I said before, is water. Okay, so now we need to write our balanced symbol equation. So copper 2 oxide, this tells us copper has a charge of 2+. We know oxygen has a charge of 2-, so we just need 1 copper for every 1 oxygen, CuO. You should have learned the formula for sulfuric acid, H2SO4. Copper 2 sulfate, copper is still 2+. Sulfate is SO4 2-, so 2+ and 2-, we just need 1 of each, Cu and SO4. And water is H2O. Now we just need to double check and make sure that it's balanced. So we just go back and forth. 1 copper to 1 copper, that's good. 1 oxygen by itself to 1 oxygen by itself, that's good. 2 hydrogens to 2 hydrogens. 1 sulfate to 1 sulfate. Sorry about the lighting. 1 sulfate to 1 sulfate, so that is balanced and we're all set. Okay. Ammonia solution plus nitric acid. So when we have ammonia plus an acid, we make an ammonium salt. So we get ammonium. Nitric acid forms nitrates, so ammonium nitrate. Okay. Ammonia, you should know, is NH3. Nitric acid, you should know, is HNO3. Those are things you just need to learn. Ammonium is NH4 with a +1 charge. Nitrate is NO3 with a -1 charge. So one ammonium will go to one nitrate. So we have NH4, NO3. All right. Now we just need to make sure that everything's balanced. We have 2 nitrogens, 4 hydrogens, 4 hydrogens, 3 oxygens, and we're all balanced. So the next one, calcium carbonate plus hydrochloric acid. So we have a carbonate plus an acid. So we're going to make a salt again. We pretty much always make a salt. So we have calcium is the first part of our other substance. So we take that for our salt. And then we take hydrochloric acid forms chloride. So calcium chloride. We also make water. And our last thing, remember, carbonates need something to do with that carbon, so they make carbon dioxide. So those are our 3 products this time. All right, so calcium carbonate, Ca is 2+, CO3 is 2-, so we need just one of each. So CaCO3. Hydrochloric acid, hopefully you should know, is HCl. Calcium chloride, Ca is 2+, Cl is 1-, so for every 1 calcium we need 2 chlorides, CaCl2. Remember, individual formulas we use small numbers, okay? Water is H2O, and carbon dioxide is CO2. So now we just need to go through and make sure that we balance it, okay? We have 1 calcium, 1 carbon, 1 carbon. 3 oxygens, 1, 2, 3 oxygens. We're good so far. 1 hydrogen, 2 hydrogens. So that's not balanced, so we need to put a 2 here. So we now have 2 hydrogens and 2 hydrogens. 2 chlorines, and we're all set. So we're all balanced on that one. And the last one, nitric acid plus magnesium. So we have an acid plus a reactive metal. So in this case, we're still going to form a salt. We've got our magnesium. And then remember, nitric acid forms nitrate, so magnesium nitrate. And then a reactive metal will form hydrogen gas. So again, you really just need to memorize the patterns for our different acid reactions. Nitric acid, you should know, is HNO3. Magnesium is just Mg. Magnesium nitrate, magnesium is 2+, nitrate is 1-, so for every magnesium we need 2 nitrates. And remember, since nitrate is a polyatomic ion, we need brackets. And don't forget that hydrogen is diatomic, H2. Okay, now we just need to make sure that it's balanced. We have 1 hydrogen, but here we have 2 hydrogens. So in order to balance that, we need to put a 2 here, 2 hydrogens. We have 2 nitrates, 1 magnesium, 1 magnesium, and we're all balanced. And finally, C, give the name or formula of the ions produced by acids and alkalis. So acids are things that produce hydrogen ions. Or you could write H+, or you could call it a proton. Any of those will get you the mark. Alkalis are things that produce hydroxide ion, which is OH-. Okay, those are just our definitions of acids and alkalis. Question 6 is about electrolysis. Electrolysis is a chemical technique whereby ionic substances are broken down with electricity is passed through them. In the space below, draw a clearly labeled diagram to show how the electrolysis of a solution of zinc chloride using graphite electrodes. You do not need to show the external power supply. It's bolded zinc chloride and graphite, so we want to include those in our diagrams, and it says clearly labeled, so make sure that it's labeled. So in class, when you did these as a practical, we used a U-tube. Okay, and in that U-tube, we filled it up with our zinc chloride, which is our electrolyte. Okay, we put 2 graphite electrodes in. One was positively charged, and one was negatively charged. So remember, our negatively charged electrode is our graphite cathode. It attracts positive cations. Our positively charged electrode is our graphite anode. It attracts our negative ions. And the last thing we need to label is our U-tube, or you could also draw it in a beaker. That would be totally fine. So we have 4 labels for 4 marks. Okay. Let me fix the lighting a bit on this one. Sorry about that. Okay. Now it says complete the table below to show what happens at each electrode. So which ion is attracted, what's the half equation, and what's our observation. So our anode, okay, attracts our anions. It's going to attract our negative ions. So if we have zinc chloride, we have zinc and we have chloride ions. So those are our 2 options. So our anode is going to attract our anion, which is our negative ion. So the chloride ion is what's attracted. Our cathode is going to attract our cation. Remember, cations are positive, like cats have paws, right? So positive ion is going to be attracted to our cathode, so that's going to be our zinc. All right. For our half equation, remember when we write half equations, we always start with ions and go to neutral elements. So we start with our ion, we go to our neutral element. Okay. Now remember, chlorine is diatomic, so we need Cl2 because it's one of our halogens. If we need Cl2, I'm really sorry about this lighting that keeps changing. All right, if we need Cl2, then we need 2 Cl minus. Okay. We have a minus 2 over here, and remember the charge on both sides always has to be equal. So if you have a negative 2 charge here, we need to add our negatives to this side so that this one has a charge of negative 2 as well, because remember we're adding or giving away electrons. So 2 Cl minus, we need 2 electrons. Now we have a minus 2 charge and a minus 2 charge. Our charges are the same on either side, so we know that we're good. Okay. Our observation, we're producing chlorine gas. So that's a green-yellow gas, or depending on the temperature, it might end up being a solution because some of that chlorine will dissolve. So green-yellow gas or solution. For the zinc, again, we start with our ions and we go to our neutral element. Okay, no diatomic here. We have positive 2 here and 0 over here. So we need to add our negatives so that the charges are equal. All right, so we need to add some negatives to cancel out these positives. So we're going to add in 2 electrons. Positive 2, negative 2 adds up to 0, and this is 0, so we're set with that. Our observation, if we make solid zinc, is that we would get a silvery or gray solid. And that would be our zinc. All right. Then we've got some definitions here. These are just things you need to learn off by heart. Might be worth making some flashcards. Define the following terms. Our anode attracts our anions. Anions are negative, opposites attract. So our anode is our positive electrode. Cation, okay. Remember, cats have paws. Cations are positive. So it is a positive ion. Okay? Question 7. The bulk of elements in the periodic table are metals. They have characteristic properties related to their structure and bonding. List 3 properties of most common metals. There are a bunch of different things you could say for this. You could say they are malleable. They can be hammered into different shapes or into sheets. They're ductile. They can be drawn into wires, is what that means. They conduct electricity. They conduct heat, or they're good conductors of heat. They're sonorous, which means that they make a noise when you hit them, like kind of like a bell. Malleable, ductile, conduct electricity, conduct heat, sonorous. I think those are the ones that I can think of for now. There might be a couple other that you could use, but those are kind of the main ones that we need to know about. All right. Draw a fully labeled diagram to show how the particles are bonded in metals. Sorry about this lighting again. Okay. So there are two important things that we need to have, which makes sense because we've got 2 marks. In metals, we've got positive ions surrounded by a sea of delocalized electrons. So we need to start with our positive metal ions. And then in between those ions, we have our sea of delocalized electrons. So they need to be shown in some way to show that they're not specifically being held by anything. They're kind of shared between all of these different metals. And then the last important thing is it says fully labeled. Don't forget that. That's a silly reason to lose marks, okay? So we label it. We have our positive metal ions, and we have our sea of delocalized, or you could say free electrons. So 2 important things for 2 important marks. If you had this picture drawn perfectly with no labels, you would get no marks, okay? So make sure that you're labeling because that's very important. All right? Part C, describe an experiment in which the metal iron can be used to find the percentage of oxygen in air. You should include a description of the apparatus involved, any readings you would take, how you would process your results to work out the percentage of air and oxygen. There are 2 methods that we focused on in class, using iron and using copper. So when we used iron, we took a beaker that had some water in it, and we put a test tube full of air with some iron up at the top. So we have air in the test tube, we have iron in the top, and we have water in the beaker. So what happens is the iron at the top reacts with the air and the water to form rust. So it reacts with the oxygen in the air to form rust, iron 3 oxide. As that happens, the water moves up the tube, and the level of water changes depending on how much oxygen is being used up. Okay, so using that diagram, we would measure the initial height of air in the test tube. Test tube. Okay. The iron would react with the oxygen in the air to form rust, and the water level would move up. Okay. Sorry, let me adjust this lighting one more time. Sorry about that. We would measure the final height of air in the tube. Okay. So then by figuring out how much air there was, how much oxygen was in there, we can find the percentage. So to find the percentage, we would take our final height minus our initial height. We would divide that by our initial height. So the amount that the height went down is the amount of oxygen that was in there. So we take the amount of oxygen over the total height and multiply it by 100 to get a percentage. So that's how we could use iron. Now if you look at the mark scheme for this paper, there's a slightly different method in there, and that's typically the method that we use with copper. We did that with copper when we did it in class. So look at that mark scheme, make sure you look at your notes on copper because you could be asked about that just as equally. But this is how I would use iron to find the percentage of air. Okay, we've got our diagram and 4 different things to get us our 5 marks. And that's the end of the paper. Good luck on your revision.